Cool. Thank you very much. So today I'm going to be giving a survey of several quantum and classical mixing time arguments, and this is meant to be as pedagogical as possible, so feel free to interrupt and ask questions. So broadly speaking, what I'll be talking about is a long-standing paradigm in classical and quantum Markov chains that some form of decay of correlations in the Gibbs state implies and is equivalent to some form of rapid mixing for Glauber dynamics or whatever your favorite detailed balanced Lindbladian is. And this is a long-standing line of work. So to cite some to mention some notable but non-comprehensive examples, perhaps some references you guys should have in mind are very nice works by Martinelli and Olivieri in 96 and 98, and also Sezzi, who kind of improved their results from spectral gaps to entropic inequalities, as we'll discuss shortly. But also, I guess my favorite example is this very nice paper by Dyer, Sinclair, Vigoda, and Weitz in 2002, who gave combinatorial proofs of these mixing time arguments, and it's what I'll be surveying, or the beginning of my talk will be about that. This is by and large the classical developments, and of course there's been several refinements to their results since then. But most of what I'll be talking about is about mixing time arguments in the commuting setting. And perhaps the reference that really started this line of work in the quantum context was a paper by Castoriano and Brandau in 2016, where they proved that for a generic commuting Hamiltonian, some form of decay of correlations, which we'll discuss today, implies that the Davies generator, the canonical commuting Lindbladian, is gapped, so it mixes quickly. And since then, a lot of people have tried to refine on their results, kind of similar to how Sezzi and Dyer refined on Martinelli's results, but with some unsatisfactory progress, even though it's been a prolific line of work since then, and I'll try to highlight some of the challenges that have arisen. And so perhaps the references there that you should have in mind are a long line of work by, by Capel, Perez Garcia, also Rouzet, around 2018, 2020, and 23. And perhaps most recently, as we've heard in the morning, commuting. We kind of have a brand new toy on our hands, which are these non-commuting but still quasi-local, or Lindbladians for non-commuting Hamiltonians. And this is, of course, the work by Andras, Anthony, and Castoriano. And since then, we've had very nice results on how high-temperature, non-commuting Hamiltonians, their Lindbladians still mix quickly. But what distinguishes their work from the rest of this timeline is that it was really a high-temperature result. It didn't really leverage, or it wasn't a reduction from a direct property of the static Gibbs state. And so I'll be highlighting how that arose, or their work, and why there's still some open questions in that context at the end. But just to recap out of this timeline, the goal for most of the talk is when can we come up with a direct reduction from a static property of the Gibbs state to a mixing time argument without having to white box open up what the properties of the Lindbladian are. And ultimately what this is asking is what are the minimal structural properties for mixing, instead of kind of just directly taking the infinite temperature limit, or the high temperature limit. Cool. So that's the broad goal. I'm happy to give some of the references later, but I wanted to say a few words about what the outline for today is. Are there any questions? I'm sure the literature doesn't make sense too concretely just yet, but I'll be commenting on it soon.
There's no work before Martinelli?
No, there's plenty, but I guess one of their contributions was a end-to-end decay of correlations implies mixing proof.
And you say that it's a quantum? It's a quantum law?
As I'll get to shortly, in some sense, Castoriano-Brandão is a version of their argument, in some sense.
And this decay correlation implies mixing is for spin, I guess discrete spins, right? Or
yeah, all this is spin systems, yeah.
I mean, there's a lot more work on that in Martinelli.
Yeah. Great. So, okay. What's the outline for today? I'm going to start with what I find to be this very elegant proof by Dyer, Sinclair, Vigoda, and Weitz in 2002. And ultimately, what they do is a combinatorial proof that some form of decay of correlations, which is more commonly referred to as strong spatial mixing, implies a block dynamics. Heat, some coarse-grained version of Glauber dynamics, is gapped. And if you're kind of initiating or starting in this literature of rapid mixing, perhaps this might be the main takeaway for today. The argument in this paper is quite elegant, and it really highlights all the intuition that we're trying to capture in the quantum setting. So then I'll comment on this paper by Castoriano and Brandão, where there they come up with some version which is similar to the strong spatial mixing, which they refer to as clustering or strong clustering. And in turn, this also gives some form of gapped Glauber dynamics. In the commuting setting, this is more commonly referred to as the Davies generator. And finally, I'll conclude with a discussion highlighting some of the open problems and generalizing their results to commuting, but so-called rapid mixing. Rapid mixing, as opposed to fast mixing, which is a technicality we'll get to later. And also plausible attempts at the non-commuting generalizations of these statements. Great. Are there any questions? Yeah.
What's the title of the first reference?
I believe it's called Combinatorial Arguments for the Mixing of Lattice Spin Systems. There's definitely combinatorial arguments in the title. Great. So let's dive in. Perhaps the kind of standard definition you could come up with for decay of correlations, you can kind of picture in the following diagram, where we have some rectangle, and I'm going to divide the rectangle, which represents your lattice of spin systems, into 3 regions. And there's some underlying Hamiltonian on the full lattice, but we're only going to restrict our attention to a sublattice of this full Hamiltonian. And the goal is to study correlation properties of the Gibbs state. So the simplest example of some form of clustering property is to look at how, or strong clustering, is to look at how correlations span between A and C. So perhaps the simplest way to think about that would be to look at a covariance under the Gibbs measure of two functions or two observables, let's say OA and OC, and to hope that they decay exponentially in the distance between A and C, up to some constant in the exponent. So if this isn't super clear, what I mean by covariance here is just an expectation of the product minus the separate expectations. Cool? Now, unfortunately, for all intents and purposes, just thinking about like static expectations under the global Gibbs state is a little too weak. In particular, the reason why is a little too weak for the purposes of establishing mixing arguments. And the reason why is because as your algorithm evolves, maybe you'll find boundary conditions which are out of equilibrium during the process, and you'd still like some form of decay of correlations to hold. So the slightly stronger thing you could enforce is that some form of covariance decays regardless of what boundary conditions you put around the box. So to modify this definition, I would just say that regardless of what boundary pinnings I put, this conditional Gibbs measure still has a decay of covariance. Let me polish this a little bit.
A and C could be very large.
Yeah. So is the definition clear here?
How do you normalize OA if it's very large?
Let's just say operator norm 1.
Okay.
In general, you could hope to put like some other norm of OA and OC here. But I'm ignoring that for now.
What is in the exponent? E to the minus?
The distance of A and C. Yeah, let's just say. Cool. Now, this is very tangible, right? It's extremely operational. It's essentially saying, look, I have this lattice of spins, and I'm going to perturb it at some location A and look at how that perturbation changes the expectation value of observables on C. And ultimately, the quantum definitions we'll be looking at look something like this. But before that, I kind of wanted to highlight why something like this already gives you some form of rapid mixing argument. And for that purpose, I'll kind of briefly sketch why this clustering property also gives you some form of insensitivity to boundary conditions. Yeah, shoot.
Yeah.
Oh yeah, this is a property just of the stationary distribution, right?
Yeah.
It's like, what does this apply for all the dynamics that were mentioned last time, both Metropolis and Cloud? What are the restrictions?
Right, so all I've said right now is, or most of the talk will be about static properties of the Gibbs state. I'll just try to mention some correlation property, and then I'll explain why that should imply some form of rapid mixing of the dynamics of your choice as long as it's detailed balanced.
Oh.
So how you pick the transition weights is up to you. As long as the ratios are correct, that should be enough.
So why are you thinking of this as perturbing A? You said something about perturbing A.
Right. I mean, ultimately, the way I think about it is that you're measuring some observable on A and you're seeing how much it affects C, or whether it changes how you would measure C. But the perturbation interpretation will be clear in the second board. I should say, really just feel free to ask questions. Like, there will be several definitions of decay of correlations in this talk. Each of them means something slightly different, but eventually we'll see which of them implies mixing and which don't.
This topology, like this is not the unique topology you can write. It could be like some kind of donut thing that you have hole inside it. How does that?
Yeah, here I always mean like sublattices, and you're taking rectangles.
And that's enough.
It's still a static property for now. Okay? Great. So what may seem rather surprising at first is that this is strictly equivalent to what is mostly referred to as strong spatial mixing. Now, this version of decay of correlations is best described in a picture. So basically, I want to consider the following experiment, where I have a box, also in the lattice, and I'll call it B. And then, suppose at some point in time, I have some boundary condition tau around the box. I'm going to single out a spin nearby the boundary, and also single out some region A inside the box. The claim is that if I were to look at the distribution at A under this Gibbs measure, but where I condition on the boundary spins being tau, and I compare this to the conditional Gibbs distribution at A, where I pin the boundary spins to be tau, but I flip the bit at U. So here is U, this like bit on the boundary. Then these two distributions, or their marginals at A, also decay exponentially in the distance between the bit I flipped and the spin at the center. And this holds regardless of tau. So in fact, I kind of wanted or like thought about starting the talk with this definition instead of this one. But this one is a lot more quantum friendly. It's really about like studying how observables, how like correlations between observables change. Whereas this one is a lot less quantum friendly. In the sense, what it's asking is that I have some conditional Gibbs distribution in a box, and I change its boundary a little bit, and I want to see how much the perturbation affects the center. And classically, these are essentially equivalent. I won't prove it to you, just perhaps take it at face value. But ultimately, what this is quantifying is some form of insensitivity to boundary conditions. And a lot of the rest, or the quantum half of the talk, will be on highlighting how we don't really have good quantum tools to quantify this insensitivity. Are there any questions about what it's saying before I move on? Meantime, I will.
So A could be very big, or the only scale is D, but in A, like A could be very big, and then okay.
Yeah. Yeah, what's special about these definitions, or one of the things that they're special, is that you could kind of put them inside an infinite lattice. Like, it's really all about this local scale. And I guess something to highlight is that part of the reason that this is so tricky is that in the quantum setting, we'll later have to see a situation in which we'll have entangled boundary conditions, but that's just a little bit of foreshadowing.
So the fact that, coming back to the fact that E can be arbitrarily large, just makes your hypothesis stronger, right? Your assumption is stronger.
Yeah, that's true. Yeah, it should also be somewhat not that impossible to see that this guy implies this one, although the converse isn't too straightforward. And the intuition for why is that ultimately what this definition is trying to capture is that you can sample from the marginal in A, and ultimately that will lead to some, that allows you to compute OA or F, and ultimately that will lead to some boundary condition between A and B. And then you're essentially comparing what G would be if you resample the interior, a conditional on this boundary, or if you just resample it from scratch. And ultimately, that's just comparing two different boundary conditions here and some observable far away in C, which is almost what this is saying, where you instead flip the entire side instead of just one bit.
Work for any dimension, and not just two, but
It's just a definition. I haven't proved that it holds at high temperatures, but that's also true. Great. So with that in mind, arguably what I find to be the most interesting part of this talk is the following proof sketch that SSM implies that some form of heat bath block dynamics mixes quickly. So what's block dynamics? In standard Glauber dynamics, let's say I'm thinking about the Ising model on a 2D lattice, and I have spins +1, minus, minus, minus. And the updates are essentially, I either flip the guy at the center to plus, with some probability proportional to the number of neighbors that disagree with me. In this case, it's e to the +2. Or I do it, or I flip it to minus. And in this case, this is energetically favorable, so it's slightly more likely. Yeah, I guess I could do this. Block dynamics essentially does this repeatedly on a large block. Effectively, given, I guess I can do it in steps, it might be easier. It's a Markov chain where I pick a random spin in the lattice. I look at the current boundary configuration around it. And you resample the box according to the current boundary. Cool?
it's no fixed size.
Yeah, let's fix some side length L. Which will later be chosen to be around log n. So suppose I consider the following setting. Suppose I'm given two arbitrary points in the state space, two configurations of spins, but I know they only differ at one location. The Hamming distance between x and y is 1. The central claim in this proof is essentially to say that you can pick the updates carefully such that in expectation, the distance after one step has decreased by some epsilon. This is essentially what's known as a coupling argument, but I won't get into too many details. But that said, I will sketch how to prove this claim, and ultimately how it uses this strong spatial mixing property. But before that, let me just kind of highlight why this contraction is enough to prove mixing. So ultimately what I'm saying here is that if I have two adjacent points in the state space, odds are they get closer. So you can kind of do this iteratively by saying if I have, let's say, t steps of the Markov chain, regardless of, suppose this holds for one step, although without getting into too many details, it's also true that it holds regardless of the distance. So in particular, let me put it this way. The distance, if the 2 points are close, I guess it's best drawn in a figure. If I have 2 points which are distance d apart in the state space, like their Hamming distance is distance d, I can couple adjacent points to arrive at their next steps, let's say, z1, z2. Ultimately, what I'm trying to say here is that the entirety of this method is to show that if the Hamming weight decreases after one step for adjacent points, then it also decreases if the points are far away. And essentially, what this entails is it reduces proving the Hamming weight contraction after t steps to proving it just after one step. So to sketch how this, or what the intuition for this Hamming weight contraction is, basically the idea is, suppose I have x and y which differ at a single bit u. Then after one step of the block dynamics, there's essentially three possibilities. Either u is contained in the box, in which case nothing happens to the Hamming weight. Or u is contained in, or u is, sorry, either u is outside of the box, or u is contained in the box, in which case, since the boundaries of x and y are the same, they'll agree after this one step. And the third possibility is if u hits the boundary of the box. And this is the only kind of non-trivial case I'd like you guys to focus on. It's essentially saying, if I have these two different configurations which differ at a very specific point, but the update depends on where they differ, then how much can this affect the subsequent configuration? And this is precisely what this definition of strong spatial mixing is trying to capture. It's capturing, I have these two different starting points and I run one update. How much does it affect a distance d away from the update? Okay. So just to dig into this latter point.
Sorry.
Yeah.
What was the relation between u and d in the block dynamics? I guess I'm just asking.
Right. I mean, okay. So in this block dynamics, it's basically I pick a random center and I update a box around that center. And here I'm saying, look, maybe I have two different configurations which differ at a single point, U. And then I run one box update around a different point, V. What happens to the Hamming weight? And there's essentially three possibilities. Either nothing happens, or the Hamming weight disappears, because these updates only depend on the boundary. And the non-trivial setting is when you update the entire box, but the update depends on the bit that they differ. So in principle, x prime and y prime, these updates could be completely different inside the box. I could have boosted the Hamming weight by a large factor. But as we'll see, like this strong spatial mixing property essentially says that away from this update, nothing really has happened in the interior. Okay, so let me just dive into this in a little more detail. What happens in case 3? So again, case 3 looks something like this. The intuition coming from strong spatial mixing is that at distance r away from this differing update, this region A, I can ensure that after the updates, let's say from x, y, which differ at u, they go to x prime, y prime. X prime, y prime agree on A with probability essentially this error. Ultimately, this is coming from the fact that if I have two marginal distributions, or two distributions that are really close, I can sample from them and ensure they agree with probability all but that error. And what this is telling us is that if I compute the expected Hamming weights change in this third case, it's bounded by this volume inside at radius r away from the perturbation, which is something like r to the dimension of the lattice. But if this coupling fails, which is extremely unlikely, I lose the entirety of the box. And you can ensure that this is ultimately polylog the box size by tuning the radius appropriately. So let me take a step back before kind of like really diving into trying to say what this argument is trying to capture. So ultimately, the challenge in establishing this mixing argument is that, as you update these boxes, you'll encounter several boundary configurations which are out of equilibrium. Like just to perhaps to highlight in a picture. At some point in time, maybe you've updated this region A, but then subsequently you update the region B in blue, and you'd like to argue that the region now AB is collectively in equilibrium, not just the individual components. And the reason that this is, I guess, conceptually challenging is because in principle, even one perturbed or like one out of equilibrium bit in B might have spoiled the entire region A. I guess to write this like in words, after updates, block updates in A and B, what you'd like is that both A and B are roughly in equilibrium with their boundaries. And somehow this is the intuition that the mixing arguments in the quantum setting will try to capture as well. So this was a lot. I wanted to.
Sorry, do you need the exponential there for this? Isn't d squared fighting d in all this?
Yeah, I mean, you mean this exponential?
In the spatial mixing.
Yeah, certainly a smaller decay would also give you a mixing argument. It's just typically phrased like this. Normally, I mean, certainly on lattices, you don't need an exponential to kill the polynomial here. Great. So I guess this took a little longer than I expected, but it's okay, because the main concept that I was hoping to convey in the second half is really what are the quantum tools to quantify this conditioning on the boundary, which kind of lead to the main techniques. But are there any questions about this classical proof before I move on?
Sorry, you showed that if x and y differ on one point, and then later you optimize R and show that they differ polylog L.
Right.
But your goal is to show polylog L is less than 1.
Yeah, that's a good point. I guess I can explain it in a little more detail. Basically, there's three kind of possibilities here. Either the block update doesn't change the Hamming weight, or it decreases it to 0 because it's captured by the box. Or you, if the perturbation or the bit that they differ hits the boundary, they differ kind of locally around this boundary. So you can kind of compute the three cases together. And ultimately, this case here, where the Hamming weight decreases to 0, doesn't contribute to this expectation. But geometrical arguments show that the probability your Hamming weight doesn't change, it still is 1. It's just 1 minus the odds this bit hits the box. And that's roughly L to the D over N. And then the caveat is that you might pay polylog L if U hits the boundary of the box. But the odds of that happening is proportional to the area of the box. So you end up having this fight between the area and the volume. And the volume typically wins. And yeah, so it might even be worth concluding the argument. Here, ultimately what you get is, if you iterate this argument t times, you get something like n 1 minus epsilon to the t. Here, epsilon is roughly 1 over n. So you get e to the t over n. So ultimately, these are t discrete time steps, or t log n, or sorry, n log n discrete time steps, which maps to log n continuous time, so rapid mixing. But ultimately, it's all captured in this coupling argument.
Then go back to Umesh's question. Seems like they do need polylog. It's really not that many.
Yeah, but there is room to have this to be
Right. I mean,
L.
Find it.
I think it's okay if this is a rapidly decaying polynomial in R instead of exponential. Let me keep that. So to pivot, I wanted to talk a little bit about the commuting case. So here, we'll be thinking about a quantum version of Glauber dynamics for commuting Hamiltonians, and that's known as the Davies generator. And Andres didn't get into it in too many details, but ultimately, it looks something very similar to what was written down, where you have some Lindbladian, and it's a sum over local terms. And each one of these local terms has this metropolis weight, and then a transition term, but also a dissipative, term. And there's no need for a coherent because it's commuting and cleanly detailed balanced. Although, I guess for now, the structure of this Lindbladian isn't too relevant. The main theorem that I'll be talking about in KB16 is that L for this Davies generator is gapped. In particular, it has a constant gap. If and only if it satisfies some form of decay of correlations, which they refer to as strong clustering. In the interest of time, however, I think I'm mostly going to talk about the main technical definition, which is how to properly do these conditioning operations. I should say, though, that if you are interested, or the goal for today would have been to describe, if you kind of carefully look at their proof sketch, there's a very nice proof that L has or a simple proof that L has a inverse poly n gap, which is quite approachable, and I'd recommend. Great. Assuming it has some form of strong clustering. So, what's the deal? So, effectively, since in principle, effectively, since in principle, there's no real way for me to fix the boundary conditions and then resample the quantum Gibbs state on the interior of the box, the right way to perform these conditionings is something of a dynamical perspective, where you first restrict your Lindbladian to given a region A. In the lattice, the idea is to restrict your Lindbladian to the jumps in that region A. And once you perform this restriction, the kind of correct notion of a conditional operation
instead of
Yes, good catch. Thank you. On some observable or some operator is simply to run this local Lindbladian for infinite time on that observable. And somehow, what this is doing classically is fixing the region and then resampling the interior of the region by looking at the boundary. So it's effectively resampling from the conditional distribution on the interior, condition on the boundary. But in the quantum setting, this is a little less clear because, well, the boundary might in principle be entangled, and since you're doing quantum measurements to perform these maps, you might actually collapse the boundary. So you are macroscopically changing it, even if in the classical setting you're not changing what's happening at the boundary. And, oops. I guess there's several nice properties about these maps. In particular, they're kind of like projections in the sense that they square to themselves. And first of all, when you compute, let's say what happens to some observable on the Gibbs state, like the expectation of the observable on the Gibbs state, since the Lambdatian is detailed balanced, you can kind of map it over to the Gibbs state. So taking conditional expectations on the Gibbs state is equivalent to just doing nothing. Great. So,
You know what the range of EA is?
yeah, so for a commuting Hamiltonian, this is actually a great point. For a commuting Hamiltonian, the range of EA is just A and the boundary of A. But if you were to apply the same framework, like the same definition to their Lambdatians, the range kind of delocalizes. It might in principle spread across the entire lattice. And hopefully if I have time, this is essentially like the main reason these proofs don't apply to the non-commuting setting.
If it's a projection that ranges the entire lattice, then maybe it's not so neat.
Yes, yeah, it is not so meaningful, yeah. There is some hope that you could truncate the time, but then you would no longer have this kind of cute property. You'd have some like monotonic version of it. Great. So with that in mind, perhaps the best discussion of why this like conditional expectation is useful is in the following like sequence of correlation definitions. What one could hope for in the context of this like paradigm of decay of correlations implies mixing is to start from the following simplest definition of what is referred to as weak clustering.
Sorry, I'm a bit confused with the notation.
Yeah.
Observable or a state?
Yeah, that's a good question. Like this is in some sense in the Heisenberg, or like, yeah, the Heisenberg
So
picture.
which means your LA is an A.
Yeah, I lied a little bit. Yeah. Great. So the weakest thing you could possibly hope for is, again, to think about covariances of observables. Let's say in some region across the entire lattice, A and C, and hope that they decay with the distance between A and C. And much like how in the classical setting this wasn't enough, maybe it implies some interesting structural properties about your Gibbs state, but it isn't enough to capture mixing. So as an intermediary definition to what actually is useful, it might even be instructive to consider what I call a slightly less weak, slightly stronger clustering. Right. So I guess I got kind of interrupted here, but it is worthwhile to think about what this definition of covariance is. Just to spell out you're computing the expectation of two observables compared to their separate expectations. Ultimately, this can be recast in terms of this conditional expectation operation. It's a little tight, but ultimately what I'm saying here is that instead of subtracting the expectations separately, you kind of subtract it in the operator, where the expectation is with respect to the full lattice. Maybe I'll just do it on the other board.
I lost track there. What's E?
Yeah, E is this conditional expectation, but without the subscript, I just mean the full lattice. And ultimately, I guess it might be just helpful to write this out. If you think of the covariance with respect to some region R of pair of observables as computing some inner product, where you subtract the expectation from those observables. Then in this language, this notion of weak clustering is just the covariance with respect to the full lattice decaying with the distance. A slightly more refined definition would be to say that the covariance with respect to arbitrary regions A, B, C also decays. And this is almost what this is capturing, as I'll discuss shortly. And in some sense, this is like a conditional variance. You're ultimately first sampling the region ABC and then computing a variance. It's also almost the these covariances with respect to the reduced density matrix.
It's conditional about it?
But if I throw I minus E onto rho, that just vanishes. Unconditionally?
Here,
Yeah.
you can't throw it because there's a product here, right? But if you expand,
But rho immediately follows. Oh, right, okay.
yeah.
So what's conditioning about? Like you said, it's like a conditional.
Here?
But how do I interpret the condition part?
Right. So it's instructive to think about what this is saying classically. And ultimately, it's effectively saying, I have these regions A, B, and C. And I'm first going to sample the boundary condition tau from the Gibbs measure. Let's say for functions f on A and g on C. Yeah, you first sample the boundary conditions, and then you sample separately A and C conditioned on the boundary. And this is, if you recall, essentially almost what strong spatial mixing was capturing, in the sense that the quantification wasn't in expectation over the boundary, but instead for all boundaries. But that said, I think it's instructive to really pause for a second and think about really what we were trying to get to with this proof strategy. Ultimately, what the proof strategy was meant to capture was the following picture, where you have the lattice and you divide it into two regions, or three regions, A, B, and C. And the goal somehow was to argue that if you do some form of block update in which you update the region AB, and then subsequently do some form of block update where you update the region BC, ideally that should be equivalent to updating ABC collectively. Like you have equilibrium with the boundary in AB and equilibrium in the boundary in BC, and that's essentially equivalent to having equilibrium across ABC. But unfortunately, thinking about these expectations in terms of products is a little non-trivial. So instead, what you can think about, or I guess ultimately what one ends up thinking about, is comparing the covariances of A, B, and C, or these conditional covariances of A, B, and C, versus conditional covariances in A, B, and covariances of BC, ultimately because they're linear. And I guess just as a matter of notation, let's say that I'll refer to a conditional variance of some observable as the covariance with itself. And in this notation, you can kind of explicitly write out what the variances of regions A, B, and C are of observables compared to the partial regions. And this is, I will admit, a bit of a mouthful, and I was hoping for a gentler lead up to this. But ultimately, the strongest version of decay of correlations that you can get to, which builds on the previous two, namely this weak clustering, which considers the full lattice, this slightly stronger clustering, which is looking at these local versions of the lattice, is a version which captures this composition of local mixing. And what KB define as I guess I was doing blue. What Castoriano and Brendel define as strong clustering is the statement that for all observables on A, B, C, and technically their boundaries, this covariance decays with the distance of B and C, or A and C. And intriguingly, yeah?
Can you define covariance of AB yet?
Yeah, it's here. The region R is, in this case, the union A, B, and C.
Right, but I guess how the R appear in the definition?
Oops. Yeah, these are like local expectations with respect to R. Somehow conceptually what this is trying to capture is that like you have some large observable on some region. This is the region R, and maybe your observable is around it. And you kind of resample the region R, kind of trivializing the observable within it, kind of pushing it to the boundary. And it's studying, or at least this variance is studying what happens after you trivialize the observable on the boundary. I'm not sure that was entirely too specific. I mean, the better interpretation I have for what's going on here is the following statement, where what you'd like to do is study what happens after you resample A, B, and then B, C. And you'd like to claim that it's effectively the same as resampling A, B, and C. And the way you can quantify it is this variance statement that says that like variance of observables on the tripartition are bounded by their variances on the individual parts. Ideally, later you would pick the length scale of B to be much smaller than the size of C.
So this inequality that you propose is true for all distribution, for all.
For all states, I mean, that satisfies. This is true in general, yeah.
That top one true for all states.
Yeah. Yeah, ultimately what this is trying to capture is some form of factorization of your variance. You have a variance on a tripartition, it suffices to compute the variance on the two sides. And what's kind of special about it is that once you take these conditional expectations, you're really just kind of localizing the operators to either side. I think I will pause, or I'll pause for a discussion here.
Oh, maybe just one more question. So that thing will not be default definition. That thing hold for even for non-commuting Hamiltonian or the unique commuting?
Yes, technically yes. The caveat, of course, is that these operators won't be local. They'll act on the full region.
It's like the point that like the difference from quantum and classical is that here you have to take it to be somehow global ones. Like O could be like touching every part of these ones. But then like
I'm not so sure. I think this is strictly incomparable to any classical definition. I mean, ideally what you'd really like to do is you'd like to perturb the boundary a little bit and see what happens to the variance or covariance of observables. But I don't think there's any good or meaningful way to do like worst case over boundary bendings. So instead there's this statement which is somewhat weaker than the classical statements, intuitively because of this. Like these conditional expectations are in some sense taking expectations over your boundaries. Right.
So are there examples of Hamiltonians for which we can prove that?
This? Yeah, it generically holds in commuting models at high temperatures. Yeah. And I think there is some belief that some form of this, I mean, generically people believe that this should hold for non-commuting models too, but for a correct definition of these conditional expectations. I mean, perhaps to highlight one of the challenges, it's really not clear how you would trade off these like nice, clean projection properties with the locality that you would need to establish this type of argument. Maybe there's some way to play with the time scales where you kind of define like a truncated time t version of this operator, argue that these non-commuting Lindbladians are finite range up to that time t, and then use that range to define like some boundary region here, but I don't think anyone's successfully managed to do that. And to highlight, I guess, part of the challenge, I think most of the discussion today was tailored towards these variance quantities. And that's because variance quantities are tightly related to spectral gaps, a part I didn't really have time to get into. But there are tighter ways to prove mixing, typically in the form of entropic inequalities. And classically, a lot of the techniques here kind of carry through. Like this form of variance, so-called tensorization or factorization, also holds for entropies, or some form of conditional entropy. But no one has been successful, even in the commuting setting, at coming up with a good definition of a conditional entropy that has a property like this, instead for unless for very specific systems.
Are there examples of commuting Hamiltonians where this proof technique is able to nail down the threshold critical data? But you need some way of proving slow mixing.
That's true. I mean, what I can tell you is certainly true is that if your Lindbladian is gapped, it satisfies this. Or like the Gibbs state satisfies this, which is also in their paper. So in some sense, it's necessary. Ultimately, it also is telling you that like the onset of these slow mixing properties or metastability coincides with the like breakdown of decay of correlations. Is another way to interpret it.
Gap means 1 over Paulian gap?
Constant, yeah. Ultimately, what people believe is true is that either you, I mean, strong clustering should imply, some form of strong clustering should imply a log Sobolev inequality, which is like rapid mixing, and vice versa. Like log Sobolev should imply a clustering argument.
Can you say something about how this, I guess how any of this generalizes beyond the lattice, like to other arbitrary graphs?
Yeah, that's a fantastic question. The short story is that okay, so typically to leverage decay of correlations, you'd like your graph to have bounded diameter. Because if your diameter is log n, like you don't really have the space to leverage like an exponentially decaying cutoff. So generically, these things, they don't hold in the same way you'd like them to for like expander graphs. But there are still some proof techniques that address expander graphs. They're just very much not based on this. They're typically just directly go to the high temperature limit.
So intuitively, should I think that this E expectation A wants to set O, the A part, to be something like identity, or something else?
No, that's exactly what it is doing. It is setting the A part to identity, but it may affect the boundary of the A part.
So this expectation A has some leakage into B. C also has some leakage into B.
Yeah.
And the idea is this B part is so large that this leakage it don't matter.
Yes. Yeah. I mean, again, the length scale of the B part can be fixed, and then you expand C however you want. I've been a little loose with the normalization factors here. You'd want O to be bounded in some norm. But outside of that, essentially, yeah, the length scale can be chosen arbitrarily.
Can you quickly summarize the difference between strong clustering, weak clustering, and slightly stronger clustering? That'd be much.
Yeah, I mean, so like this weak clustering are like covariances with respect to the full lattice. The slightly stronger version of it is where you like look at subsystems, like conditional expectations with respect to subsystems. And this version is trying to capture what happens when you sequentially take expectations. It's significantly less clear than the other versions because there's no immediate classical analog to this.
And strong clustering?
Oh, that's what I mean by it. Like it's really meant to capture what happens when you apply these projections one after the other.
Ah, okay.
What is the counterpart of the saying boundary doesn't matter? That you mentioned.
Yeah, so I mean, this version is kind of saying that on average the boundary doesn't matter. It's full transparency. It's not clear to me how this is capturing like a worst case over boundaries, and my understanding is that it actually isn't. But right.
I guess it's just like O could be anything outside. Like N and EC, they actually overlap outside EC.
Yeah, that's true, but they agree in some sense.
But
He's just emphasizing that the observable O need not be contained to ABC. It could also lie on the boundary or in principle outside the boundary, although only the boundary really matters.
I thought you said for any O on ABC.
Yeah, it was a little misleading. And the boundary.
yeah, I guess we're done. So I guess we already have lots of questions and it's a very nice discussion. So I think we're over time. But any more question, or I guess lunch? Okay, and thanks, Thiago.